This is John Black, Super Chemist. This video is part of a new updated playlist called Time, and the name of the video is How to Calculate Gamma with No Graph. First, let's just do a couple problems. This is the first problem right here. Got three light years in between here, and then they give you the velocity that you're going at. You're going at 0.6 c. Gamma equals hypotenuse over vertical line. Your time you got by touching a gravity machine compared to the time that you would have by standing still. And then we take that down to a something over 1, which is itself. Every problem, all you need is this triangle here. You draw this triangle. It doesn't have to be perfect. You don't care about the lengths or anything. You just care about the numbers you're going to assign to those lengths. Now we need to know the hypotenuse, and we need to know the vertical line. We don't have any numbers here. What are we going to do? Okay, hypotenuse is horizontal line over your velocity. So what does that mean? You know that I shouldn't even have to tell you this. You know, this is because look at these guys. If you're walking or on your spaceship, let's just say walking, are you going to be walking here? Are you going to be walking here or walking here? And look, it's right touching this line. They're parallel. I have it. It should be intuitive that this is the line that you travel on. The horizontal line is what you did. You went. Where did you go? You went 3 light years. So that's 3. The velocity they gave us. They actually set the problem up right here. It's 3 over 0.6. We know that 5 times 6 equals 30. So 5 times 0.6 equals 3. This is 5. 5 times 6 equals this. So we put our 5 up here. Now we need the vertical line. Now we go here. This is basically Pythagorean's theorem. I rearranged it and I changed the A and the B so that they're X and Y, because we care about X and we care about Y because we're trying to find the resultant basically. But we need to know what its ratio is to the standing still. This is not 5 to 1. So basically we just plug in our numbers here. C squared we know was 5. We just figured that out. So that's 25. X squared we know it's 3. They gave it to us. That was given. So that's 9. The difference is 16. We square root both sides and we get y equals 4. So now we have the vertical line. We put it in there. And so you don't need a calculator for that. That's 1.25. Your gamma is 1.25. If you were standing still, a second would go by. If you started moving like this, yeah, this is still 1 second, but only in your frame. You know, if you compare it to this second over here in a standing still frame, it's 1.25 longer. This distance is longer, and therefore, and this determines the second, how long a second lasts. So therefore, I mean, this is 1.25 times bigger than this line. So let's go down here and do the second problem. We got the same setup. You got the little triangle. You got your hypotenuse equals horizontal line over velocity. So here's your problem, though. Here's your spaceship. This is a common problem because the sun, the closest sun, I think, is 4 light years away. Okay, so they always give this one. They always say 0.8 c. So what do? Again, we do the same thing up there. It's already set up right here. It's already set up. So we just put our 4 here and we put our 0.8 here. 5 times 0.8 is 40. I mean 4. You know, just like 5 times 8 is 40. So we know that's 5. So we put the 5 over here. Now we need the vertical line. This is the new second. We want the second. What would happen if we were just standing still? So again, we go to Pythagorean's theorem. That's already rearranged. C squared we know it's 25. The x squared we know it's given. 4 squared is 16. The difference is 9. Square root it. Y equals 3. Vertical line equals 3. Your standing still line equals 3. So you put that in. So we write our 3 in there. It's 5 over 3. We simplify that. It's 1.66. That repeats forever over 1. So our gamma is 1.67. It's that simple. It's that easy. You don't have to use any of this crap. You get the same exact answer. I want you to see what is going on here, though. I want you to see that this is the standing still second. This is your moving second, or the second that you get because you touched a gravity machine. Here you weren't touching any gravity machine, no acceleration. You're just floating there, just standing still. But I want you to understand something else. This here is, you're just figuring out two vectors, man. This is your resultant. Your hypotenuse is your resultant. We've done this. If you're in physics, you know what I'm talking about. You want to break these down into a x component and a y component. Why? Because when you're standing still, the photon or the information carrier has to go up and down in between the photon clock plates, or your synapses in your brain, your neurons, your atoms in a mechanical clock hand. It goes back and forth, say this way. So now you said that you moved this. You went in this dotted line here, right here. You moved. So now, what does you only are moving this way. So what? But what about your photon? Your photon is not only moving this way, it is still moving this way, because it still has to go from one photon plate to another photon plate, going back just like this. Or a neuron in your brain, right? Or two atoms in a clock hand. They're going like this, but they're also going this way because you're moving. See? So that makes two vectors. Two vectors. I want you to notice on this problem right here, when you divide these, this is 4 light years divided by 0.8 light years per year. That's your velocity. The light years cancel out, you're left with 5 years. But this right here isn't really 5 years, it's 5 light years. The photon, in normal circumstances, if 5 years goes by, it goes 5 light years. But we wanted, so this is a fact. Photons move at, 5 light years per 5 years. That's a fact. So this 4 light years, that's the x component, and this is the y component. The y component, you were going to do that anyway when you were standing still. You get this is useful. You are transferring information with your information carriers. So you get no time dilation. A second is, as short as it can be. It's a regular second. But this here, this causes your time dilation, the x-axis. This is not useful. Okay, they're both useful, but they're not both useful when it comes to transferring information. This y-axis is totally just transferring information. This is basically just trying to keep up with you moving 4 light years, 8.8 c. That's all this is about over here. It's not really useful for transferring information. It's just useful for keeping your photons and your information carriers caught up with your velocity of going 0.8 c. But the photon isn't actually going this way and this way. It's not doing that. It's doing this. It's going this diagonal way. It's just that these two are components or whatever of this. When you break this down into x and y, do you same down here? Do you understand that this hypotenuse is your resultant? Why? Because your photon had to go 2 directions, this way and moving through space this way. So you're going like this. The photon is not going in little steps like this, so that it only goes in the x and y direction. Okay, it's going at a diagonal line. So this is just a resultant. This is just a resultant. And when you have an x and a y vector, how do you get the resultant? How do you do that? You use Pythagorean's theorem. That's all we're doing. Even this. This is just a rearranged equation that used to be and still is Pythagorean's theorem, just like mine is. If you combine these, because really this and this aren't actually the same, because this is finding the vertical, the standing still time. This is finding the hypotenuse, or the moving time. But all equations, mine, theirs, whatever, are still just different forms of Pythagorean's theorem. his equations. Pythagoras' equations can be used to find different things. You can find the horizontal, the vertical, the hypotenuse. So you have to take this equation and this equation, these two equations, or these two equations, and combine them. And then the combination would be the same exact thing that's going over here. It's just that mine seems simple and easy and intuitive, and this does not. You don't have all this crap, no giant numbers like c squared. This is you almost don't even need a calculator, man. Come on, you can almost do this in your head, kind of. Especially this first part. Come on, man. This first part, you don't need a calculator for that. Now because here's gamma, right? Hypotenuse over vertical line, right? Moving over, standing still, touching the gravity machine, not touching the gravity machine. And these are all equal here. This is the gamma that they give us right over here. Now, if I wanted to confuse you, this would be my formula. The two formulas I gave you, this one and this one. This is just a combination of them. Okay, if I wanted to do it like this, okay, because this tells you the top and this tells you the bottom. This is your hypotenuse. This is your vertical line. This is your hypotenuse. This is your vertical line. This is your stretched out second or moving second, the guy that's touching the gravity machine. This is the guy just floating in space. He's inertial. Same over here. But you see, I wouldn't do this to you because this looks complicated. This looks screwed up. Okay? This over here is very intuitive, especially the way I drew it and everything I did here. Everything should be intuitive to you. And what is inverse gamma? It's 1 over gamma. This down here is inverse gamma. This is their inverse gamma. It's not 1 over this. Now it's just this. My inverse gamma is the vertical line over hypotenuse. And this is basically a percentage. Remember the 1.25 up here? That was your gamma. So now we put it 1 over 1.25 and we get 0.8. This is our inverse gamma. That's a percentage, 80%. See here, the hypotenuse times 0.8 equals the vertical line. The vertical line is 80% of this length. And you can see over here, this is the inverse gamma and this is gamma. For gamma, the hypotenuse is 1.25 times the vertical line. 5 is 1.25 times bigger than 4. And then the inverse gamma, right, you got vertical line, is 80% of hypotenuse. 4 is 80% of 5. Remember, hypotenuse equals moving time or touching a gravity machine time. And vertical is standing still time or inertial time because you are not touching a gravity machine. And down here, remember you had a gamma of 1.67, so you do the inverse is 0.6. That means your hypotenuse times 0.6 equals your vertical line, because your vertical line is 60% the length of the hypotenuse, just like it says down here. Here's your hypotenuse is 1.67 times time bigger than the vertical line, because 5 is 1.67 times bigger than 3. Just like up here, the vertical line is 60% of the hypotenuse. Yeah, because 3 is 60% of 5. So I hope you understand how gamma and inverse gamma work. In the last video, these were all the same. Everything on this board is the same formula. The rocket, the rotating thing, and the Earth. They're all gravity machines. They all cause acceleration. They all cause you to move through space-time or space faster than you would normally do. You would be standing still. And this makes the distance between the plates on a photon clock greater, or the atoms in a hand on a clock, the distance greater, or the distance between neurons in your brain greater when you move. And if the information carriers are forced to move at sea, then the information carriers will take longer to travel to deliver the information. And what is this information for? It's for physics. So this slows down all physics. This is one of the many, many, many reasons we know Earth is an accelerating frame of reference. because you get time dilation. It is not possible to be time dilated without acceleration. That is the first step.